So we've seen that the diazonium salt is an important intermediate that can then be converted to lots of other things. You can convert it to a hydrogen, you convert it to a phenol, you can convert it to any of the halogens or a nitrile group. So how is it that sodium nitrite and HCl reacts with an NH2 group to form that diazonium salt in the first place? Right? Once you have the diazonium salt, we propose that either the nitrogen falls off and you actually generate a carbocation on the benzene ring, or perhaps the nucleophile that's going to come in here kind of attacks this position and pushes negative charge into the ring, and then nitrogen gas leaves. Nitrogen gas leaving is obviously the best thing. It doesn't have to be an aromatic amine for NaNO2 to react to form the diazonium salt. Unfortunately, aliphatic diazonium salts tend to be really unstable, so synthetically it's not particularly useful. But it is an important reaction. There's an intermediate on the way here, which is a nitrosamine. And the N-nitrosamines are implicated in cancer. In fact, aromatic amines in general are well-known cancer-causing agents. The two top chemicals on the list of suspected carcinogens are both aromatic amines. One of them is this one, which is benzene. And the other one is the naphthylamine, beta-naphthylamine or 2-naphthylamine. These are number 1 and number 2 on the list of suspected carcinogens. There was a benzene spill at a chemical plant that was making benzene, and the incidence of bladder cancer among those exposed to the benzene was 100%. Every single person that was exposed to those high concentrations of benzene developed bladder cancer in the end. I have the unfortunate distinction of having worked with both of these compounds in my past research, so I'm hoping I don't get cancer. But 2-naphthylamine is a really pretty pink, kind of needly crystal. It's a really attractive compound, but it's also going to cause you cancer. I do that as a public service announcement, so that if anybody suggests in your future that you should work with either benzene or 2-naphthylamine, you should make sure you're doing it in a hood with gloves and trying to avoid exposure. Right? So these N-nitrosamines, because preserved meats often have high concentrations of nitrites. If you look on your bacon package, sodium nitrite is a major ingredient in there. And when you're cooking these compounds, you tend to have aromatic amines in there. The presence of the nitrites will make N-nitrosamines. So if you've heard that bacon causes cancer, the reason they think bacon causes cancer is because of the formation of N-nitrosamines because of the preservative, the nitrite that's in there as a preservative. Pepperoni, all the really nice tasting pork products have this problem that they're cured and preserved with nitrite, which is very good as an antibacterial, but also reacts to form these nitrosamines. So we want to know how we make this into that, and then once we have that, how we make it go all the way. The nitrosamines of aliphatic amines are fairly stable, whereas for the aromatic amine, generally, you're not going to isolate that. You're going to go all the way to the diazonium salt. So let's think about the mechanism. What probably happens when we mix this stuff together? First step, of course, would be to be successful in drawing a good Lewis structure for the nitrite ion. Right? If you don't have a good Lewis structure for the nitrite ion, you're done before you start. And unfortunately, drawing Lewis structures is not something that people are very good at. So that's a weak base. We have aqueous HCl. What we're trying to do is form nitrous acid. And because nitrous acid is unstable and gradually breaks down in aqueous solution, we have to form nitrous acid by mixing together the nitrite salt and the HCl. Of course, in your stomach, there's HCl and there's nitrites if you've just eaten a big stick of pepperoni, so you're going to form nitrous acid. So what do you imagine might happen to nitrous acid in a strongly acidic aqueous solution? And by analogy, what happens when we mix nitric acid with concentrated sulfuric acid in the nitration reaction? This oxygen grabbed that hydrogen and we formed an intermediate that looked like this. Basically protonated nitric acid, and then it broke down, right? It grabbed this hydrogen here. We did that. And we formed this cation, the NO2 cation, right? NO2 plus. Well, if nitric acid can do that, nitrous acid can probably do it as well. Nitric acid is a stronger acid than nitrous acid, so nitric acid is actually less likely to get protonated than nitrous acid. So chances are good that in aqueous acid solution, we can protonate nitrous acid. Which oxygen are we going to protonate it on? Probably that one, because there's a resonance structure that looks like this. Not a very good resonance structure. Right, but there is that minor resonance structure. So let's protonate this oxygen. Now we've got a protonated form of nitrous acid. It's not too much of a stretch to imagine that this can do exactly the same thing that does, which is it can grab this hydrogen and generate the nitrosyl cation and water. Right, so we've got NO plus, no plus. Basically it looks like carbon monoxide, except that it's got a nitrogen there instead of an oxygen. That's one extra proton. So that nitrosyl cation is what's actually going to react with the amino group. So if you know how to generate the nitrocation, you know how to generate the nitrosyl cation. Now we'll redraw this with some. Remember, the minor resonance form actually has an electron deficient nitrogen, right? So it makes sense that this would attack at nitrogen rather than at oxygen. To generate something that looks like that. first step, once you've generated that nitrosyl cation as the electrophile, is to do a nucleophilic attack on the electron deficient nitrogen. And we're one step away from the nitrosamine. After we deprotonate the ammonium ion. Right? So that's pretty simple. So nucleophilic addition. Now what? So this is one of those mechanisms that's going to be mostly a whole bunch of proton transfer steps. Eventually, you're going to lose that as water. Right? And you're going to form the nitrogen-nitrogen triple bond. So basically what we need to do is we need to start taking protons off nitrogen, which we just did, and putting them on oxygen instead. So steps 2 and 3 of this mechanism are to remove the proton from the nitrogen and put it on the oxygen. This mechanism starts to look a little bit like the Wolff-Kishner reduction. That's not surprising, because in the Wolff-Kishner reduction we had the same thing, right, where we were taking protons off a nitrogen atom, putting them on an oxygen atom so we could lose water. This obviously has a resonance structure, pretty good resonance structure. That has a double bond to the nitrogen. And has a neutral oxygen. You can't form double bonds on both sides because that would be expanding their cation nitrogen, and that's not allowed. But I think it's easier now that you see this resonance structure to imagine that the next two steps are probably going to be take the hydrogen off this nitrogen and stick it on that oxygen. We can now do the pushing out of water and the forming of the triple bond between the two nitrogens. And this whole time chloride has been watching. As a spectator ion. So it was a few steps of just kind of proton transfers and loss of water to generate this nitrosyl cation. Then you had a nucleophilic attack and a deprotonation to generate the N-nitrosamine. And then a series of proton transfer steps, protonate oxygen, deprotonate nitrogen, protonate oxygen again, followed by the loss of water to generate the diazonium salt. Almost all proton transfer steps except for the first step here, which is the nucleophilic attack to form the nitrogen-nitrogen bond, and the last step, which forms the nitrogen-nitrogen triple bond and loses the water. Make sense? Pretty straightforward, right? Proton off, nitrogen on oxygen, off nitrogen, on oxygen. We had to do the same thing with the Wolff-Kishner reduction, where we had hydrazine attack the carbonyl carbon, then we protonated oxygen, deprotonate nitrogen, protonate oxygen, so we could lose water. Pretty common theme. Once you have that diazonium salt, we know that it can be converted into lots of different substituents on the benzene. But that diazonium salt can also react at the nitrogen atom. So if you apply Great Rule of Organic Chemistry number 1 and draw the ridiculous resonance structure, right? People are going to look at you strangely if you actually draw this resonance structure. But that doesn't mean that there is no resonance contributor for that resonance structure. You'll notice that the nitrogen on the end here is actually electrophilic. This one's not, because you can't make another bond to that nitrogen. That would be 5 bonds. But this one is. So if you have an activated benzene ring, like phenol, for example, and you have a diazonium salt, the benzene ring can actually attack the diazonium salt. Now a base can take that hydrogen off, probably water. And this rings, this link here, where you have that nitrogen-nitrogen double bond between 2 aromatics, azo compound. And there's a whole class of dyes and coloring agents that are azo compounds, azo dyes. There are indicators that are azo dyes. So for example, I believe that one is called methyl red. It's got a sulfonic acid on one group and a dimethylamino group on the other side, and it's this azo dye in the middle. It's pH dependent. It'll be red on a certain pH or yellow on a different pH. But you'll notice that it's got this really long extended conjugated pi system, because this pi system here is now linked to this pi system by the pi bond between the 2 nitrogens. That extended pi system results in a lower gap between your orbital energy levels, and that's what pushes your wavelength of light that's going to be absorbed to cause that electronic transition into the visible range. So azo dyes can be made from the diazonium salt if, when you're forming the diazonium salt, you have an activated benzene ring in there along with it. And that concludes our discussion of azo diazoniums.